So in this video, we'll be talking about the properties of liquids and the factors that affect these properties. So the first property we're going to talk about is viscosity. So this may be one of those terms that you have actually heard in real life and you have actually used in real life. So for example, whenever you see or you're dealing with something that's very thick, for example, honey, you'll hear people say, or you may have said yourself, oh, this is very viscous. And that's exactly what viscosity is. So it's a liquid's resistance to flow. So the more viscous something is, then that means that you're saying that it moves very slowly, right? So it all has to do with IMFs, right? We talked about intermolecular attractions slash IMF, same thing, and how those attractions are what brings molecules together. And it ties directly into this. So when something has very high IMFs or very strong IMFs, it's going to have a higher viscosity. And if you think about it, that makes sense, because if these molecules want to like gather together, then obviously they would also want to stay together versus interacting with a surface, right? Or like dripping off of a surface. And the major thing I want to point out here is that shape does affect viscosity as well. So to illustrate that, I want you to look at this list of hydrocarbons. So this list of hydrocarbons has the shortest hydrocarbon to the longest hydrocarbon. So pentane has 5 carbons in it, and then nonane, I say nonane, I don't know how it's actually pronounced, has 9 carbons. But the point of this is that if something is a shorter chain, then that means you could technically say it's like rounder, right? Versus something that's longer and longer, it's not as spherical, right? So molecules that can roll around more easily, in other words, shorter ones, they will have less surface to surface contact, which means you have less attractions, which means you will have a lower viscosity. So if we look at the viscosities for both of these, we will see that for pentane we have 0.24 compared to nonane we have 0.711. So there you can see how something that's smaller, more spherical, less of a long chain, it's going to have a lower viscosity. So a factor that affects viscosity is temperature. So the higher the temperature, then the lower the viscosity. So I used to be like an analytical chemist at a pharmaceutical lab this past year. And I would have to measure properties, physical properties and chemical properties of different, liquids and materials. And I would have to work with this material called polyethylene glycol, and it's very thick. And we would heat it up so that we could measure the viscosity. And the whole point in that is that the increased molecular motion, so the more heat you put into this material or molecules or whatever it is, you make it easier to overcome the IMFs, so it's going to start flowing. So that's why we would heat it up, so that it would flow a little bit, so that then we can measure the viscosity. But anyway, the point of this slide is to show you how, for example, with water, as we increase the temperature, right, you see a decrease in viscosity. So at 100 degrees, we have 0.282. At 20 degrees, we have 1.002. Another property of liquids is cohesive forces. So you most commonly see this, for example, whenever you look at just water droplets, wherever they may be. In this picture, we're showing you like a spider web, and then there's water droplets on it. So what is holding these water droplets on these tiny little fibers of spider web? So it's cohesive forces that's holding those together. So IMFs between identical molecules have cohesive forces holding them together, right? Cohesion, it's like something that's very well put together. That's what I think of when I think of cohesive. So when molecules in a liquid are surrounded by their identical like selves, they're going to be attracted to each other all equally. So for example, here we have like a cluster of water molecules, and you can see how they're all attracted equally to the ones around each other. But something that will happen is at the surface, the molecules only feel half the forces. So here I want you to look at this diagram compared to the one right here where it's surrounded. This one that's surrounded feels IMFs from all around it, compared to up here it's only half, right? Up there it feels air. So what happens is that molecules will minimize the surface area by forming droplets. They want it the least amount of surface area as possible so that they can have more cohesive forces between them. So that's what happens whenever you see droplets. It's the fact that molecules are doing that on purpose to minimize surface area. Another property of liquids is surface tension. This also kind of has to do with the same idea about the surface area and how it is affected by IMFs. So the energy required to increase the surface area of a liquid is called the surface tension. So if you've taken bio, you've probably heard of this, but it's the reason that certain bugs can walk on water. So here in that picture, you can see that this bug is just like standing on water. And this has to do with the fact that these molecules would rather stick together than be pushed apart. So it has to do again with IMFs. And you can see here how water has an unusually very large surface tension. So mercury, if you've ever seen mercury in a picture, or if you've ever actually seen it in a thermometer, I have certain times where there happens to be like an old thermometer floating around in the lab, a mercury thermometer, because those are really like outdated already because they're so poisonous. You know, if it breaks, it can be poisonous. But when you see it, you see the little droplet of mercury, like it just stays together as a little droplet. It's really weird. And that has to do with the surface tension. And same thing with water. It will form droplets, and it will have like things floating on top of it because of that surface tension. So another thing I want you to think of is how whenever you put water or water spills on certain surfaces, it doesn't necessarily like wet everything, right? So for example, here is a windshield that has like a coating of hydrophobic, some product that you can like wipe on it versus uncoated. And you can see how the water like sticks to one of them better, and that is the uncoated. So that has to do with the adhesive forces between the water molecules being greater than the adhesive forces between the water and the hydrophobic repellent. So water would rather stick to itself again in comparison to the hydrophobic coated glass. So another property of liquids is capillary action. So capillary action is whenever liquids can flow up a thin tube despite gravity. So it's really weird. Like if you have this very tiny thin tube, and let's say you place it on top of water, the water will start crawling up. So it's kind of scary, right? Because it's going against gravity. But the narrower the tube, the higher the liquid. This also has to do with some previous properties we talked about, the cohesive and adhesive. So cohesive forces will hold the liquid of the molecules together. The adhesive forces attract the outer liquid molecules to the tube surface. So for glass and water, water really likes glass. It's very attracted to it. So that's what you see happen. You place the capillary tube in the water, and then it will start rising up. Compared to mercury, it can't do this. It doesn't have as high adhesive forces. So whenever you place the mercury inside, it would actually like lower, and it's called capillary repulsion. So molecules in a liquid are always moving. They're not moving as fast as a gas, but they're always moving. So just picture them in here, crowded, moving around. But if the energy of these molecules are at the surface, they can actually end up having enough energy to end up overcoming these attractive forces. So the ones right here at the very surface will have a chance at evaporating. So the larger the surface area, the faster the rate of evaporation. Once they evaporate, they escape the liquid and they become a vapor. So that's what you see up here. These are water vapor molecules. So whenever something changes in a chemical environment, things don't just stay like static. And we're going to discuss this, further whenever we get to this chapter, but there's something called dynamic equilibrium. And whenever things change, like I said, in a chemical system environment, things will not stay static. They will shift in order to relieve or reduce the effects of the change. And this is exactly what happens whenever you have vaporization happening. Like for example, in a liquid, some of the molecules will start to evaporate and they will go into the gas phase above the liquid. And let's say this is a closed system. What will happen is that the process of vaporization will be occurring at the same time that condensation is also happening. So the same way that these molecules can break free from the surface and turn into a vapor, they will also condense back into a liquid. So this happens together, and this happens in a dynamic equilibrium. So the rates will eventually meet each other so that they reach this dynamic equilibrium, and they will eventually end up being the same. So let's say again that you have a liquid and you have a closed system and everything's in dynamic equilibrium, so the rate of condensation and the rate of vaporization is happening at the same time. The rate which molecules are escaping from the surface turning into a vapor, and the rate which molecules are condensing and turning back into a liquid is exactly the same. Now whenever this happens, you will have a pressure exerted by the vapor on top of the liquid, and this pressure is called vapor pressure, right? Makes sense. So two things that you should know, or like one major relationship: the weaker the attractive forces, the higher the vapor pressure. How can we reason this? So the weaker IMFs you have, then the less the molecules are going to want to be around each other. So think about IMFs as like molecules wanting to be around each other. High IMFs, they really like each other, they stick together, they hang out a lot. Low IMFs, they don't like each other, they don't care if somebody leaves, right? So they don't care if something turns into a vapor, so you're going to have more vapor, which means you have a higher vapor pressure. So the higher the vapor pressure, the more volatile the liquid. So volatile liquids, you can think of like, for example, when you have like 100% acetone, if you're taking off your nail polish, or if you've ever seen somebody take off nail polish, it evaporates like right away. It has a very high volatility. So in this example, we will be explaining vapor pressure in terms of IMF. So what do we need to know for this? We need to know about London dispersion forces. So every single molecule has London dispersion forces. We have dipole-dipole. So polar molecules have dipole IMFs between them. And then finally, hydrogen bonding. And I'm summarizing everything because I'm hoping that by now you have watched that video and you know probably what these acronyms mean. So hydrogen bondings, you have to have OH present in your molecule, or FH, or NH. And in this case, you will see that it's in particular OH. Okay, so we rehashed that. Now, how do we apply this to these molecules we have? So given the shown structural formulas of these four compounds, explain the relative vapor pressures in terms of types and extents of IMF. Another thing we also have to know is that for London dispersion forces, the larger a molecule is, the more London dispersion forces you have, right? So keep that also in mind. Now we know every single one of these has LDF, so we can cross that off our list. Now, which of these has dipole-dipole and hydrogen bonding? So I hope also that you notice right off the bat, we have some OHs. For water, we have technically 2 potential OH sites, right? So the 3 of these can hydrogen bond. So that right away is going to tell you that diethyl ether will have the highest vapor pressure. So this one will have the highest. Now, why is that the case? It's because it has the lowest IMFs. It only has LDF in comparison to everything that we already know has hydrogen bonding, which is the strongest of all the IMFs. Okay, so we established that. Now, between all of these, which one would have the highest and which one would be like in between? So another thing that you can use to rank is how many points of contact where you can have hydrogen bonding. Ethanol only has 1 point of contact right here, versus ethylene glycol and water have 2. So we know that ethanol is going to be right up after diethyl ether. So this one would be second lowest IMF. So again, it would be second highest VP. So I'll just write second lowest IMF, but you can like determine that relationship from the IMF. Okay, so between water and ethylene glycol, which one of these has the highest IMF? So because ethylene glycol is bigger, so remember we pointed that out earlier, when something is larger it has more LDF. Because ethylene glycol is bigger and it has those 2 points of hydrogen bonding contact, it is going to have the highest IMF, which means this would have the lowest vapor pressure. And then water would be in between, so it would be third. So we would have the second lowest vapor pressure, same thing. So these are the types of problems, again, that you'll be expecting from chapter 10, very descriptive, where you have to reason things and rank things.